You know, when you think about solar power, you probably picture those big blue panels, right? They're basically just fancy plumbing for electricity. But nature's been using sunlight for billions of years for something way more interesting, chemistry. A leaf doesn't have a power cord. It uses sunlight to literally create fuel. And today, we're diving into how we're learning to do the exact same thing. Some of the things this technology can do sound less like science and more like, well, magic. Get this. Imagine a powder that you just sprinkle into dirty water. You shine a light on it, and it just eats the pollution. Gone. Or how about this? A window on a skyscraper that never, ever needs a window washer. The sunlight hitting the glass is enough to break down all the grime, and the next time it rains, it's just washed away. The window cleans itself. And here's the real holy grail, the one that sounds like straight-up science fiction. You take a jar of water, add a pinch of a special catalyst, and just leave it in the sun. And you watch as it starts bubbling, splitting water molecules into pure hydrogen, a totally clean, storable fuel. So what is going on here? Is it magic? Nope, not at all. It's actually something way cooler. We're going to break down how all of this is possible, and it all comes down to the weird and wonderful world of quantum mechanics. So the little engine at the heart of all this is a material called a semiconductor. And the absolute best way to get your head around how it works is to picture it as a tiny two-story building designed just for electrons. Okay, so you've got the ground floor. We call it the valence band. This is where all the electrons live. They're stable, they're comfortable, just hanging out. Then, way, way up top, you have the penthouse, the conduction band. It's a high-energy party spot that's usually totally empty. Now here's the most important part. There are no stairs. An electron is either on the ground floor or it's in the penthouse. There is absolutely nothing in between. So how does an electron make that huge jump? It gets a powerful kick from a packet of sunlight, a photon. If that photon has enough energy, bam, it punts an electron from the ground floor all the way up to the penthouse. But it's not just about the electron that goes up, it's also about what it leaves behind. That negative electron leaves behind an empty spot, a vacancy that acts just like a positive particle. We call it a hole. And this is where the action happens. That one photon has just created two powerful chemical soldiers, a super high-energy negative electron and a really strong positive hole. When they get to the surface of the material, they go to work. The positive hole is like a voracious electron thief. It rips electrons off of nearby water molecules, creating these tiny molecular buzzsaws that just shred pollutants to pieces. At the same time, that high-energy electron reacts with oxygen, creating even more buzzsaws. It's a total pincer attack on grime. Now, I know what you're thinking. This sounds way too perfect. If it's this simple, why isn't every building in every city already coated in this stuff? Well, it's because there's one single, massive Achilles heel that has plagued this entire field for decades. It all comes down to basic physics. Opposites attract. That high-energy electron up in the penthouse doesn't want to be there. It is powerfully, desperately drawn back to that positive hole it left on the ground floor. And if it falls back down, a process we call recombination, that precious solar energy is just gone, wasted as a tiny puff of heat. The electron jumps up and then plummets right back down in a fraction of a nanosecond, long before it has a chance to do any useful chemistry. It's the biggest bottleneck in this entire technology. So pretty much the entire history of this research has been a hunt for a clever way to keep these two apart long enough for them to do their job. And that brings us to the hero of our story, a really elegant and ingenious solution called the Z-scheme. You see, the early attempts to solve this problem involved a pretty bad compromise. Sure, they could separate the charges, but only by making the electron way weaker. And that meant it just wasn't powerful enough to do the really tough jobs, like splitting water to make hydrogen. The Z-scheme just flips that whole idea on its head. It uses two different materials. One material is amazing at making super strong electrons, but its holes are kind of weak. The other material is the exact opposite. It makes really strong holes, but its electrons are weak. Then comes the brilliant part, a strategic sacrifice. The Z-scheme is designed to force the weak electron from one material and the weak hole from the other to find each other and cancel out. So what does that leave you with? The strongest possible electron and the strongest possible hole, perfectly separated and ready for action. And that's why it's called a Z-scheme. If you trace the energy path of the electron, it jumps up, drops down a bit to recombine, and then the one that's left over is way up high. It looks just like the letter Z. But here's the most incredible part of all of this. We didn't invent it. Nature did. This is exactly how photosynthesis works inside a leaf. We are literally reverse engineering a plant. Okay, so we've solved the recombination problem, and we've managed to keep our electrons as powerful as possible. So what? What does this actually let us do? What becomes possible now? Well, it also solves a second major problem. See, most of those early catalysts were really picky eaters. They would only work with high-energy UV light. The trouble is, UV light only makes up about 5% of the sun's energy. That means these materials were completely blind to 95% of the sunlight hitting them. All that energy was just being wasted. The Z-scheme is the key. It lets you use two different materials that both love to absorb that abundant visible light, and then it stacks their energy together. So you get to use the entire solar spectrum and produce these super high energy electrons. It is the absolute best of both worlds. And this is where it opens the door to a completely remade world. For energy, we're talking about making clean hydrogen fuel from nothing but water and sunlight. We could even turn CO2 from the atmosphere back into methane fuel. For the environment, you've got self-cleaning buildings and even asphalt that can neutralize oil spills. And in health, imagine self-sterilizing surfaces in hospitals or on subways, where the overhead lights are constantly killing bacteria. The real takeaway here is a total shift in how we think about our cities and our technology. Right now, a city is basically a machine that eats energy and spits out waste. With this tech, a city could function more like a forest. But let's think even bigger. Imagine a spacecraft on a years-long journey to another planet, where you absolutely cannot afford to waste anything. Imagine if the interior walls, powered by just a few simple lights, were constantly purifying the air, scrubbing the CO2, and recycling every drop of water. A ship where the walls quietly do the breathing for you. That's the kind of future this technology is building.